Okay, on stage and sound, cool. Now we should be good to go. So, no one puts Java in a container. So, I was asked to give a second talk, and I really like this topic because it's actually something we see often in production use cases where customers run into problems. And maybe just to start, what is this talk is about? So, who of you knows this quote, "No one puts baby in the corner"? One hand? Oh, come on. Okay. Who of you can maybe relate to this scene? Dirty Dancing. So at least in Dirty Dancing, there's this one scene where baby is put in the corner, and then Patrick Swayze comes and basically rescues her out of the corner with this quote here: "No one puts baby in the corner." And so this talk is not about Dirty Dancing, and it's not about not running Java in a container, but it's about the pitfalls of running Java in a container, because it's not as straightforward as you might think. Containers are really cool for a lot of stuff, but there are some like downsides to especially running Java or applications who haven't been written to be run in containers inside containers. So this is what this talk is about. I already introduced myself like an hour ago, but just for those people who are still sleeping then. So I'm a distributed systems engineer at Mesosphere. And so that means I'm mostly working on the Apache Mesos project, which has now been presented twice already today. And so there I'm a core contributor. And if I'm not there and not in China, I really like giving talks about those technical challenges and about like this ecosystem, especially like containerization and Docker, for example. Why do I so much care about Docker? If I personally am working on the core, so I'm more like a C++ person. And so why do I actually now give a talk about Java and Docker containers? And this again relates to like DCOS or Mesos, which we've seen before. And this is the only slide I'll show about DCOS, I promise, in this talk. And just the message I want to get across with this slide is that a lot of people there was a question by you before, how many people actually run workloads in Docker containers on Mesos or DCOS. It's not restricted to Docker, but still there are like a lot of people running Dockerized applications, running Dockerized Java applications on top of DCOS or on top of Mesos. And when those guys run into problems and then we get asked to support them, that's why I personally care about this topic so much. All right, containers. We already established, most of you know what containers are, but how many of you know like the lower level concepts like C groups, namespaces, this kind of stuff? There's some hands, but not all hands. So I would like to start with a short introduction of those topics. For those people who know all of this by heart, this gives you like another 5 minutes of sleep maybe, but otherwise it's building up to like the challenges related to running Java in a container, so I feel it's important to understand those concepts. So containers, as mentioned before, they're a really cool tool to package applications and basically write once and then run it anywhere to a certain degree. That's at least the promise containers are giving to us. And let's just see to which degree this promise is holding true. And actually, many of us who are working with like Java, we have heard this promise before, right? With Java, write an application once, run it everywhere. So let's see how those two combination of promises, they combine inside Docker containers. And containers, on a high level, they actually appear like a lightweight virtual machine. And this is also like when going to customers and we ask them, what is your motivation to switch over to containers or to switch over to DCOS to move containers? A lot of them basically say, yeah, we actually want to reduce our VMware licenses. And so from a high level perspective, it feels a lot like a virtual machine. You have your own process space, own networking interface, you can install packages, you can run services, you can actually SSH into a Docker container. So feels a lot like a VM. But actually, to those people, I say really be careful, because on a low level, it's something very, very different. So it's actually like C root on steroids. So it's not a VM. all of it, it's running on the same operating system kernel. So if you manage to screw up that kernel, you'll actually screw up all containers running on the same box. And it's a bunch of processes just visible on the host machine. So if I'm admin on the host machine, I can actually see all processes running in those containers. Whereas when I use virtual machines, each of them gives me their own operating system. And so I don't see from the host OS or all processes on the different guest OS. And I also, if I screw up one kernel from within my virtual machine, all my other virtual machines, they're still going to run. So it's different, and if you consider replacing your VMware licenses with containers, really think about your use case. In some cases, or actually probably in many cases, it might be okay, but if you really need this deep isolation level between different containers/virtual machines, then you might want to reconsider, because in my opinion, virtual machines, they still have a valid use case and they're not replaced by containers. So maybe just to summarize this idea, or the difference is basically with virtual machines, I have like an own guest OS for each of my virtual machines, whereas with containers, they actually share the host operating system and the host kernel between all the applications. And actually what a container then does, it just ships its own binaries, all the dependencies the application needs to run, and then uses like those underlying kernel features, which we're going to see in a second, as namespaces and C groups to both provide like visibility to basically make it appear to each container he's owning the entire machine, and also isolate resources between different containers. And yeah, let's actually from what's going to happen if I run a Docker container. This is what I mentioned before. It's like all the processes, they are visible from the host operating system. So if I do like a Docker run nginx, and then actually check which processes are running, I actually see those are just processes all running on the same kernel, on the same machine. So I, as an operator of the host machine where it just executed the Docker run command, I can actually see like all processes which are running there, and can also see here like my nginx running on the same machine. All right, and so to summarize, like the differences are and what you should consider when choosing between virtual machines and containers. On the other hand, containers, they have weaker isolation guarantees. In most cases, this might be actually okay, but if you're, for example, if you need to run your Coca-Cola and Pepsi workload on the same infrastructure, you should make sure that not the only isolation level is a container in between those two companies. Otherwise, they might get a little unhappy about it. Therefore, containers, this weaker isolation level actually gives you benefits on the other hand. So, for example, containers, they actually, as we saw before, it's just like a process on the same kernel. So it's running at near native speed for both CPU and also like I/O, and that's like quite a benefit even to like modern virtual machine technologies, which still have like a considerable overhead. And the other advantage is that also like launching containers, it's like really fast in the so if I use libcontainer directly, I benchmarked that a while back, you can get like in tenths of a second I have my container running. Whereas with virtual machines, also that has improved quite a lot. So especially if I'm not just considering VMware, but for example like KVM, I can also spawn up like virtual machines in like a second range. But it's still like containers are considerably faster to spin up. And of course, as with containers, I don't have the operating system replicated across all my hosts. So I actually also have like less storage, because yeah, of course the operating system needs storage, and also like memory overhead for managing all those, for running all those operating systems on top. All right, once we've seen that, keep in mind there's still like so many use cases, and I personally also like containers. This is not going against containers. This is just the warning slide. Containers might not be right for everyone. But yeah, let's actually talk about container isolation, putting people in the corner, which is what this talk was about, right? putting someone in the corner is actually about isolating him from like the rest of the class or the family if he has done something bad. So let's actually see how containers manage to provide isolation guarantees. And so if we look at like how Docker, for example, is working, we have those kernel features underneath here, C groups and namespaces. And actually the interesting bit is that Mesos has like its own containerizer since like the early days. And actually that's depending on the same parts. So we also use C groups and namespaces internally. And actually what we can do since the 1.0 release, we can run Docker images without relying on the basically those two parts here, and basically run them natively using the Mesos containerizer, which underneath uses the same features for years. So that's just to symbolize this underlying guarantees, and what a Docker image eventually is something really simple. You can also use without the Docker runtime. All right, the two stacks we saw there are namespaces and C groups. Namespaces are basically used for providing different isolated views on the system. So each container can see its own view on like process IDs, on network, on user IDs. So there can actually be like several times the same user ID. So I can have multiple users with user ID like 10, for example. Same for processes, because each container, each namespace can start with like from scratch counting upwards for all those IDs. Control groups, on the other hand, they're actually used to control access to resources. So this can both be used for limiting access. So it can be, for example, here with memory, I can limit the amount of memory someone can use, or it can actually also be used for accounting, to just account how many cycles does this container have used over like the last minute, for example. And we're going to see that in some more detail. Maybe just what I like as a special C group is like the freezer one, which actually allows me to just freeze the task. So it wouldn't receive any CPU shares anymore, which is something quite useful, which we also use internally when we spin up new processes or want to kill processes. And yeah, basically just freezing a process group by not having it receive any CPU shares. So this is also something control groups give you, and therefore containers which implement or which utilize those control groups do. Control groups is also like the next part I want to dive into a little deeper. And as said before, it can be used for both limiting access and also for an accounting part. And actually it's something, as in Linux, Unix, something really simple. It's just like a hierarchical system, a hierarchy, a tree, and you can also just see the folder level. You can just do an ls on it, for example. And inside this, I just call it now folder hierarchy, if you want to view it as that. In this hierarchy, there can be actually several subsystems. So each of the subsystems we saw before, for example, for memory, for CPU shares, for CPU sets, and each of them has its own like hierarchy. And what's kind of important, that each process can, in each of those subsystems, just be once. And that's basically the level at which it is isolated. So each process ID at like one level of this hierarchy, it's considered as like one group of resources sharing the same resources. So the second part, as mentioned, is like the accounting part. And here I can really use C groups to keep track of, for example, metrics. If I want to keep track of different process groups, for example, how much memory did they use, how much pages did they write, how much memory was evicted, how much stack is used, and so on. I can actually do that on this process group level, which makes also like accounting, if I internally have to issue like cost to certain groups, that I can actually use the accounting principles here. And then the second part is the limits, where it can have hard and soft limits. So soft limits, they're not enforced, and there's some discussions whether they're useful or not. but basically hard limits, they'll actually trigger and they'll manage that you're, in case of memory, that you'll actually be killed. And this is something, if you are a Java developer, this is something we're not used to. So in Java, if we use too much memory, we're used to basically getting an out of memory error. If I run inside a container and I'm using too much memory, like more than the outer Docker container / the process group is allowed to use, I'll simply be killed. I don't receive an out of memory, I'll just be gone basically. And yes, just like one example how we can set those limits. So it's basically like just the 128 max here I would use for my Fedora in this case. CPUC groups. So CPUC groups, it's basically, I again have the metrics part, which I don't really have time for to dive into, but like the limitation types, they're kind of relevant because I have two different subsystems here. First of all, I have CPU shares, and then I have CPU sets. How many of you know the difference? Okay, some hands, but very few. So let's actually check that, what's the difference, because it's relevant. So CPU shares is actually, it's a priority weighting across all the cores. The default value, which if I don't specify anything, it's going to assume it's 1024. And I can actually specify other values. So for example, if I use Docker run with like the value of 512, this Docker container has less priority of CPU shares compared to a Docker container I would start without that, because it would start with 1024. So if I have two C groups created here, and one C group basically has CPU shares 768, and the other one has 256. That actually means that the CPU shares, assuming nothing else is running on the system, that C group A is going to receive 75% of the CPU shares, whereas the C group B is going to receive 25% of CPU shares. Just consider if we now would cancel C group A again, C group B would again receive 100% of CPU shares, but it basically means this is a way of getting a relative meaning between different applications. CPU sets are slightly different. So CPU sets are actually pinning your process group to certain CPUs, and they're going to reserve CPUs for this specific application. This is, for example, if you're running in like a NUMA setup, this is really useful because in a NUMA setup, you often want to bind your application to certain cores, so you're not switching too much in this NUMA hierarchy. And this, for example, if I do Docker run CPU set 046, that actually means I'll be using those 3 CPUs for my Docker container, and they're actually going to be reserved for me, and yeah, I own them to that degree. Namespaces. Namespaces are, as mentioned before, those different views on the system. So for example, if each container should have its own view on like the process ID, so they don't have to consider like conflicting process IDs across 2 containers. And each process actually by itself, it's running namespaces. So even though I just started a simple Unix process, it's going to have its own namespace, so to speak. It just like depends on the parameters I actually fork a process with, which namespaces I actually enable for this new process. So, but that's time-wise is going to go into too much detail. So let's flip onto process ID namespace. So each process ID namespace actually is starting at 1. And 1 is also like the special one for each process group, because it means if that process ID 1 is going away, the entire process group, so the entire namespace is going to be killed. So whenever I would fork a process saying I want a namespace or process ID namespace, I'm going to get this new process ID 1 for my fork process. All right, switching over to Java. Just a short question, how many of you are like Java developers? Quite a few. Yeah, I said I'm on the C++ side, but Java is still pretty cool. But similar as Docker. Like Docker is consisting of several parts. Docker actually has the Docker runtime, the Docker image format, plus like all the networking stuff around it, or additional specifications. And similarly, Java is actually consisting of several parts. It's the Java language, it's the Java specification, and it's the Java runtime. And here we're mostly going to talk about the specific Java runtime, because that's actually what's relevant if I want to run it in containers, because I'm going to put the Java runtime into a container. And Java memory, so what's actually all contributing to Java memory? So many of us, or I guess probably all of us who ever ran like a Java application, we know how to set like the maximum heap space, for example. But there's actually a lot more memory footprint whenever I run a Java. So there's the native JRE overhead, there's the perm and meta now metaspace, there's the JIT, who actually also needs resources, and also if I use JNI, I also have a lot of memory overhead, and also Neo. Neo is basically so fast because I'm working in like more native memory, which is not constrained to the heap, and also threading gives me a certain memory overhead. So that already sounds like we need to take care a lot if we want to set memory limits with Docker containers. And one thing which many people, or which I personally feel it's like a trade-off with like the latest Java version, it's basically they have moved from like this perm space to metaspace. And the permanent perm space before, it used to be constrained. And now what's actually happened is that the metaspace is actually, it's just constrained by the system amount of memory you have available on your system. So that already sounds like a very good way of crashing your system using your Java application. So if you have like a bug in your class loaders and you're filling up this metaspace, this is an easy way now to crush your entire system, and not as before, just crashing like your JRE. Of course, it's running in native memory space. So here it sounds like it might actually make sense to run Java in a container, because if I have a container limit for this, also the metaspace is going to be constrained by the container limits. Okay, cool. And now just let's take a look a little bit how the JRE is actually managing CPUs. So there are actually a lot of initializations. So whenever I start up a JRE, based on the core count available on the machines. So it's the number of compiler threads, the default number of compiler threads I use for my just-in-time compiler. It's used for a lot of hotspot thresholds and optimizations. Also garbage collection, the default number of threads is based on the number of cores available on the machines, and so on and so on. So there are actually a lot of decisions based on this core count available on the machine. And many of you might already get a feeling this might be challenging inside a container, and it actually is. So let's actually bring both worlds together, containers and Java. And let's see then actually where Java is getting the CPU information from. In like Java 7 and 8, in JDK 7 and 8, it's read out of the sysconfig. And that means whenever I run that in a container, I'm going to get the total number of processors available on the system. So imagine I run on a 32 core machine, but my container is supposed to use only 4 of those. I'm still going to get a count of 32 for all those initializations we saw before. With JDK 9, that changed. So actually, they are now using getAffinity. And getAffinity is actually considering CPU sets. So that's like an advantage. So in this case, actually, I think I have a slide for that, right? Yeah. So actually, in that case, with the example we had before, like 32 cores in general, for my Docker container, I would actually get what I expect. I would only get 4, and all those initializations are based on 4. So with CPU sets, so basically, again, if I would run Docker like this would make the difference between Java 7, 8, and 9, how many CPUs Java or the JRE would consider it can use. same with basically CPU shares, which you should be aware of. With CPU shares, it's always going to, if you use CPU shares, it's always going to give you the total number of CPUs available on your system. So if you have a huge box where you're running your Java application on, you should be aware of that basically the JRE in each of your containers is going to be initialized with this potentially very high number of cores. All right, this is the example with like the 32 cores we had before. So it's basically 32 cores are going to be seen by the JRE and going to be used for defaults. So this is something you can override most of those defaults, but you should just be aware of that you should do that when running Java in a container. So really be aware of all those defaults which you potentially need to override. How about memory? So memory constraints are even more problematic. With CPU, we can actually override a lot of this stuff, but with memory, it gets like a lot harder because there's no API to tell the virtual machine, so Java, the JRE, how much memory it's supposed to use. And like one of the rationales behind that was that the Java developers, the JRE developers, they were afraid that people might actually lie to them about how much memory is available on that node. So they might tell them too much and basically screw up the overall system. So that's why basically managing memory is even like much harder. And there isn't yet like a full complete solution. So there's some internal discussions in like the Java JRE community of introducing an API like that, basically enabling the system to run nicely within Docker containers. But if you run Java within Docker containers right now, the problem you're basically having is that it's going to see the overall memory availability on the machine and not in your container. So if you run like Docker -m and try to constrain it to just using like 1 GB of memory, Java won't really see that, this limit you're setting there. And so maybe just as a conclusion, I really like this quote. So the good thing about Docker containers, and therefore also for running Java within Docker containers, is that they don't hide the underlying hardware processes like a VM technology would do, because it's all running on the same kernel. And as we saw, we still have the insight of like the overall CPU count. We still have insights about the overall memory footprint, and we can actually use that for some optimizations. The bad thing, it's actually just the downside of that we can't constrain it to our containers, and we need to set defaults or introduce new APIs, enabling the Java to be aware of the limits which are being set by a container and not the limits which are set by the overall system we are running on. And that again gives me 2 minutes for questions.
Any questions?
No questions. How much of that did you know before, or how much of that was now new and interesting to you guys? Did you know everything before? Yes? Oh, sorry for you. Okay. All right.
There are some cans in there. So.
Cool. Then, if there are no further questions, there's.
So if I understood correctly, you are saying that running Java inside Docker containers today is a bit risky. The JVM could crash.
I wouldn't say it's risky, but you just need to be aware of it. So it's not like container. So the usual promise a container is giving you, you can just put it in there and you don't have to care. With Java, it's actually something different. So you should be aware, and you need to adjust your applications. So you should set more defaults, and you should configure your application or your JRE to be aware of the constraints it's running in. It needs to be aware that it's stuck in the corner.
One more?
Are there similar limitations for different programming languages, programming stacks like, I don't know, Node.js or Python?
Those systems, so for example, Go, which also gets some of those counts, they already use like the container-specific counts. So, and with Python, it's mostly about the interpreter. There I'm actually not aware which count he's using, but actually why it's basically coming all together with Java is first of all because so many people use it and so many distributed systems are written in it. And secondly, because they have garbage collection, they have just-in-time optimization compilation. So there's actually like a lot going on in the background. So that's why I first believe it's specifically interesting to Java, and it's probably also happening in some other programming system styles or language systems.
I have another question. The fact that you need to make JVM aware of that it runs in a container means that you're not, or you will not benefit from dynamic configuration of the limits of the Docker image running on the host.
Yes.
So that means that every time, yes,
yeah.
every time you change, you would like to change those limits, you also would need to rebuild the image.
Yes.
To benefit from that. So have you seen any kind of pragmatic approach to that in companies, how they deal with this?
So I've seen like some scripts which basically generates this configuration based on the environment they're running, because this promise we're having here, right, runs one everywhere. It makes a difference whether you run this Docker container, which is constrained to 1 CPU and 512 megs. It makes a difference whether you run that on a 64-core machine or on a 32-core machine. So what I've seen in practice by not too many people are like scripts basically adapting the configuration, but it's all like pretty hacky. And I'm really happy that the Java community is getting aware of this problem and really tries to integrate it. So we've seen this one change for like CPU sets between Java 8 and 9. I think it's even like in one of the later releases of Java 8. And we're seeing also that there's discussion going on for the memory. So that's actually where I personally believe this approach should be solved.
So that would mean that only JVM 9 would be kind of more appropriate for use in containers, right?
No, it's just with Java 8, you should set a lot of default parameters. You should override them. Like the default thread count for garbage collection. You should set it to the number of cores you actually have in your Docker container and not use the default, which is like the overall core count on the machine.
Thank you.
Okay, thank you so much. One more question. Quick.
Did you try to use LD preload library that overrides syscalls to get a number of CPU cores?
No, and I'm personally not sure whether that's such a great idea, because it's basically, it's again this like write runs everywhere. It means that you're just outsourcing the problem, right? So no, I haven't, and I need to think about whether that's a good idea. And first sight, I'm kind of skeptical.
Okay.
Unfortunately, we'll have to leave the rest of the questions, sorry, for the lobby, discussion lobby. So thank you so much, Jörg, for your presentation.